Hi folks, and welcome to Open Analysis Live. We're back finally, a few months in hiatus, but today I think we have something pretty interesting for you guys. I'm going to be talking about a loader that was used to load Emotet. So this was an intermediate stage that was dropped after a malicious document was executed. This middle stage was dropped and it was actually used to load Emotet, which is itself a loader, pretty convoluted. But we're going to be talking about this middle stage, and it's very interesting, probably one of the more unique loaders that I've seen. I've dubbed it PrnLoader, and you'll see why if you stick around. Before we get to that, I feel like I owe you a small explanation as to why we've been away. So I've moved, as you can see behind me, a new office, and we're also doing renovations here. So it's taking up all my time. Also, I didn't put this out there, but unfortunately our other bulldog passed away a few months ago. The snuffly guy who used to sleep in the back of some of my videos, and we have a new bulldog which has 1,000% more energy than our old guy, and he's just basically taken up all my time, that with the renovations. But hopefully I'll be posting back a little bit more routinely as I kind of get on top of some of these personal things. So with that, let's jump into the sample and I'll show you why it tickled my fancy. So I actually came across this because of David Ledbetter from Twitter. I is avid user of UNPACME.
UnPackMe, a malware unpacking service from Open Analysis. Expose the malware before it exposes you.
And he sent me the sample saying, hey, you don't unpack this, take a look at it. And so I did, and let me show you what I found here. If we pull up our UnPackMe results here, we can see we've uploaded the sample here, and we do have an unpacked child, and it looks okay. I mean, there's no imports for it, so that's kind of usually a sign that there's something a little bit wonky, but you know, it looks okay. When I download it though and take a look at it in IDA, I can see there's something is very messed up. So let's show you that right now. So if we load up the child sample here, you can see that there's some issue here where it's not able to translate a relative address. If we continue, we load it up and we can see it's just totally garbage. So clearly, we unpacked something that looks like a PE file, but it's not quite correct. It's not a real PE file. So it has the same structure, but something's definitely wrong. So this made me want to investigate the parent sample a little bit more and try and figure out what was going on. So if we take a look at the parent sample here, we can see that somebody had actually uploaded it to AnyRun. Very good Sandbox, awesome tool if you guys are looking to quickly triage malware. So you can see that they uploaded a doc file, and when the doc file was run, it ended up spawning a few processes. So we have this certutil.exe was triggered from WinWord to run it. Then we have run DLL32, which drops this, which is obviously being used to run DLL, and then that drops this temp file that's in exe and executes it. Now, the one that we're particularly interested in is this run DLL32. Let's go to the full run here. So then we can see here, run DLL32 is used to run this PDF, obviously a DLL, and they're passing it the IN export. So this is just, this is the standard syntax for run DLL32. You have the DLL followed by a comma, followed by the export that you want to execute. So we're assuming this sh1.pdf file is a DLL, and then this actually drops that temp file. So if we look at the hash for the KSH1 PDF file, we can see that the hash of it is actually the same hash as the file that was uploaded to UnPackMe. What's the best way to show this? So if we go to files here, and if we click on the executable, it's going to show you that hash here, FB07, whatever. So you can see that's the same hash as the one that was uploaded to UnPackMe. So just a quick bit of context for you guys to see where this came from. So this was, like I said, an intermediate stage. You had a malicious document. You can see here it was being executed. That did some stuff. And then there's this middle stage, which is the DLL. And then that dropped this temp e4 whatever .exe. So now that we have that context, let's actually take a look at this intermediate file in IDA and see if we can figure out what's going on with it. Coronavirus. We saw there was probably a PE file of some sort of structured PE file in it that we were able to extract with UnPACME, but it wasn't a valid PE file. If we look at this, one last thing to look at before we open up an IDA, we can see there are some resources in this file, and there's an RC data resource, and it's pretty big. You can see here. Usually when I see that and it's a packed file, or it's a file that is like a loader, and I see an RC data resource that's pretty large, I usually assume that that's where the packed PE file is going to be. So I'm going to check that out when I first open up the file in my tool suite in Windows. So I'm going to show you guys the resources, and I'll also take a look at it in IDA. So let's pop over here. We'll load it up in IDA. Okay, so it's a DLL, so we're going to have to look at the exports. And we can see here there is an IN export, just like what we saw in any run. So that's the one that we want to check out here. Now you can see they do actually find resource, load resource. So they're actually pulling something out of the resources, just like I suspected. So what we can do here is let's open Resource Hacker. It's a favorite tool for looking at PE resources here. And let's take a look at this RC data resource. Okay, so something very interesting. It looks kind of like a PE file. So we can see like the DOS string here. We can see that actually the first byte is an M, but then instead of MZ, we have MN. Very interesting. So it looks like this is some sort of obfuscated or lightly encrypted PE file in the resources. So now we expect that this loader is probably decrypting that PE file and loading it. Now, at this point, the process is pretty clear. We're going to have to go through and figure out how they're actually loading the PE file. But something is making my little radar tingle here.
Something's fucky.
So we ran it through
UnPACME.
which, you know, it's pretty good at unpacking stuff. And we unpacked something that looked like this PE file, but it wasn't quite correct. Now, if this loader was a simple, you know, decryption routine that decrypted this resource as a PE file and then ran it, I would expect that UnPACME should unpack it. So the fact that it didn't unpack a valid PE file is telling me something is going on here that I want to look into. And it definitely is, which is why I'm making this video. So probably what I'm going to do here is I'm going to pop over into our X-rays view because it'll be easier to see the decompiled code. So I'm just going to press F5 here. And this is actually going to be a good tutorial for what to do when you see something like this. So a decompilation failure with IDA is probably one of the most annoying failures you can have. So if you say, okay, it didn't decompile it. So this means that IDA isn't able to determine the function setup properly, and so it can't decompile it. It means that either it's off with the arguments on the stack, or the calling convention is wrong, or something is wrong here. So what we want to do is we want to fix the calling convention and the number of arguments to make sure that it's correct. How do you do that if you are lazy? The best way to do it is to try and get IDA to decompile some of the functions that are within the function that won't decompile, to hopefully try and set the number of arguments correctly for that function itself. And I'll show you the way to do this. So basically what you want to do is you want to find your call functions here. You want to pop into them and see if they'll decompile. So F5 this. Now this failed. So we want to go a little bit deeper and see if there's anything in here that we can decompile. So let's F5 this. So that decompiled. It looks like this is just a setup, like a class setup, our pseudocode here. So let's pop back. Let's F5 and see if we can do xrefs. So press X for xrefs and see if we can decompile the functions that called this function. So it might fail, but it looks like it worked in this case.
Hell yeah, hell yeah.
So we're able to, by decompiling those functions that were called by this function, we were able to kind of reset the number of arguments and rearrange the stack for the parent function. And then that was able to kind of reset this a little bit. Now, if we go back and we do an xref here, and then we can decompile. This was the main export that we were just looking at. And you can see here, it's going to complain. I was going to complain. And normally if I was being careful, I would try and figure out why this happened, but I don't really care. because we have enough to go on here to analyze the sample. Okay, so I'd like to arrange my IDA windows so that the assembly and the decompiled view are side by side, and I like to synchronize them. And I also like to view the assembly in a text view format so I can see the offsets, and it's just a better way to view it if you're viewing them side by side. So let's go back here to our in export, and now we have a nice side-by-side view with the assembly and the decompiled code here. So you can see what I was showing you earlier, where they're trying to get the resources. They load a resource, they lock it, and they copy the contents of it into this var 15. So we're going to call this, we're going to rename it with the n key, n var resource data. Okay. Now, if we look down here, we can see it looks like it's being written out to a file, and it looks like the file name is, where do we see this? Create file. The file name right here is temp e47 blah blah blah.exe. So just like what we saw in any run. So it looks like we're getting closer to the answers here. So they're writing out that something to that file.exe, and then they're creating a process for it, so they're launching it. So that's how they're actually executing the payload. Now we want to find out what they actually write into the file. So they are writing this resource data in, which, like I just showed, was that sort of malform PE, but they must be doing something with it before they write it out, otherwise it would be a malform PE and it wouldn't run. So there must be something going on here. And we can see there's 3 functions that we need to take a look at that are called before they write the file. Now you might be wondering, well, they don't pass this var resource data into any of these functions, but remember the function calls were messed up when we decompiled it, so we can't really infer anything by these arguments. They could be wrong. We need to actually take a look at the functions first, and that may fix up the arguments so we can see that this is being passed to one of them. So let's take a look at the first one here, which you guys saw a second ago if you watched me decompiling. And in this one, I'll move this over so you can have a better view. This is where PrnLoader gets its name from. So looks like they're doing a pretty standard call out to basically grab a web page here. They're doing internet open URL, and this is very strange. So it looks like they're setting up a buffer here, and instead of just clearing the buffer or setting it to nulls, they have this very bizarre setup where they where they set it all to nulls in a big array, and it just, I think this might have been what was causing the decompiler failure. It's just crazy. So I'm just scrolling down to the bottom here. Yeah, anyway, why did they do that? I don't know. I don't know whether it's a compiler optimization that's gone wild or whether somebody actually did that. I'm not sure. Anyway, so once they open that URL to that site, they read the file in. There's the file. If you're unsure, if you're wondering, like, how did I know that's the buffer, you can hover over it and it's going to show you, IDA will hopefully show you the arguments. So you know the first one is the handle, and then the next one is the buffer, and you can hover over it and it'll show you that's the buffer. So we're going to name this var URL buff. And so they're basically reading in that buffer, and they're doing something with it here. Which I believe is moving it over into another buffer. Yeah, so they're copying it over, and copying it over into this guy here, which they are then copying into here. So this is a little bit convoluted, and I'm not going to go into the details of why they're doing it, mainly because I don't want to take the time to figure it out myself. But basically they're using one buffer to read the stream of internet data in a loop. This whole thing here is a big loop, and they're reading in chunk by chunk of that buffer. They're then copying it into another buffer, and then they're copying it into this final buffer, which they're going to do some work on. So what kind of work are they doing? Well, let's take a look at the data first. You can already probably guess what they're doing here, but let's take a look at the data from that HTML page first. So what they're doing is they're grabbing this page right here, and they're grabbing it, just the raw HTML. So why don't we grab the raw HTML as well? So let's do a curl for this, and we'll paste it into this file.txt. I'll just make it a text file for now, and we can change it to HTML if we want. once we take a look at it. So let's take a look at it in VI. So we can see that it is HTML, and it's just a big long string, no line breaks or anything like that. And we can see right here, file, this little setup of JSON for the sources. And if we look back at our IDA here, something caught my eye. Let's look, once they have that HTML code, they're passing this in, sources, file, and then they're passing this in. I think that this is trying to get the location of this string and this string in the HTML. And if we take a look here, it's stir. So that's finding the string within the buffer, the location of the string within the buffer. So let's just name that, and we'll pop back here. So this is going to be offset to the URL that they're trying to locate. This is going to be the var, main var, and the URL. And if you're wondering why I'm calling it a URL, let's take a look at that HTML again. So here's where they're starting. That's where they're finding the first offset to. What's this? Well, it's actually a big URL string, and then they've used a label, close quote, comma, label to find the end of it. So this is the string that they're actually looking for in the HTML code. So let's copy that out, and let's use wget to grab that. It looks like an MP4 video. It's going to take a little while to download here, and while it downloads, let's take a look at what they're doing with that URL. So I assume they're grabbing it, so that must be the beginning of the URL start. And it looks like here they're doing the URL start to URL end, so they're probably copying that URL over here. Let's see what they're doing. Yeah, they're doing a move. So then this is going to be the URL, I believe. Okay, and they're assigning that var URL to arg2 of this. So this right here, arg out URL. All right, it's gonna take a minute to decompile. Definitely that long buffer setup is hurting IDA here, I can tell. And let's name this function while we're at it. So we'll name it malware get URL from HTML from porn. And I won't actually open that site. Yeah, I will. It's too funny not to show you. So if you're wondering why am I calling it PrnLoader, let's take a look at what they're actually downloading here. I see our download is still continuing. Let's pop over to our browser. Get ready to censor. Oh, it's porn. I don't know how I'm going to censor this in the video. It's probably just going to be a big pixelated screen that you guys see. Anyway, it's some gross porn thing that doesn't even look all that interesting. Anyway, it's still downloading. So I'm assuming that this is actually the MP4 for the porn video. I can double check once I've downloaded it. And I'm curious why they're doing that. So let's take a look at what they do once they've got the URL from this porn site. So let's pop back here. This is the URL, so let's name that var porn URL, and they pass it to this function here. So let's take a look at what they're doing with it in this function here. So they actually do download that MP4 video just like what I'm doing here. So they do an internet open URL. They have one of these buffer setups. Good Lord. They do an HTTP query info A, so this is actually getting information about the internet resource. And they use, they pass it the information characteristic, or the info level 5. And info level, show us the query flags. What's it, 5? Is HTTP query content length. Okay, so we can turn that into a macro here. Just again, press M, new, query content length. Okay, so IDA has this nice thing where they'll replace the constant with the with macro name, so we can see that it's content length. This is the buffer that receives it, so we're going to call that var download size. So they're getting the size of the file that they're going to download, and they pass it to this thing here. This is like a C++ thing. They're basically parsing out the size from the buffer that comes back. So this is the actual size. Var download size. So once they have the download size, they're doing something strange here. So they're checking to see if the size is greater than hex A and 1, 2, 3, and 5 zeros. And if it is, then they're changing the size to a hex and 5 zeros. And then they're adding it to this, they're changing, so this is actually a pointer. So we'll name this as var download pointer to the download size. Okay, and then what are they doing here? They are checking to make sure A3. So what is A3? Oh, we've added an argument here. Let's go back, let's name, I'm not really sure what this is. Let's go back and see what A3 actually is. Hey, look at that. So this is actually the size of the resource, which is kind of interesting. So remember what I said, you can't actually, before we weren't able to see where that resource data was used before it was written to the file. Well, we can see now that IDA is learning more about the arguments for these functions as we're decompiling them, it has added these arguments here. So we now know that this is a var pointer to the resource data, and this is the var resource data length. Okay, so let's name this arg. Okay, so now we're getting somewhere. Scroll down here, download size. So if the resource length is less than the download size, they create this sort of division thing. So this is var, and this is the div download size by resource. So they're getting the division of the download size by the resource, and they do it again, they do it twice. Okay, so we'll just tack a 2 on the end here. So if the, it's bar 34, oh, if we get the info, that's just an info flag. Okay, so if they got the info about the download size, if the resource length is less than the download size, they create this this division of the how many times the resource goes into the download. If it goes in less than, what is this? Less than 1024 times, then create a new variable here, which is 1028 minus the modulus of this div download. Okay, so what they're doing here is they're basically reducing the size of the download by the offset of the division between the resource and the downloaded file. So the best way to think about this is basically they are aligning the resource length as a multiple of the download file. So if the download file is this long and the resource goes into it X number of times plus some remainder, they actually remove that remainder so that it goes in an even number of times. Knowing what they do next, as soon as I've showed you that, I can explain why they do this. But let's just leave it at that for now. We'll go through this and then it should become clear to you why they're doing this. So I'm going to call this the new size of the var new download size. And it's no surprise that what are they doing here? They're now downloading the download up to that size. So so they're downloading that portion of the download file, not the whole thing if that condition up here was correct. So if the resource was smaller by many multiples than the downloaded file, they actually truncate the downloaded file. So this is their buffer here. Is that the buffer? I'm not sure. I see what they've done here. So this is actually the pointer to the buffer. This is the download buffer. This is the download buffer counter. So they create a copy to the download buffer. So they've, I'm just cleaning this up a little bit so it's easy to read. So they basically use internet read file to read the new size of the download into this download buffer. They read it in chunks. That's what the while loop is for here. Once they've finished reading it, they create a pointer to the beginning of that buffer, which they then use down here in what looks like some decryption. And so now we get to the key part of this malware. So once they've downloaded that buffer, which we have downloaded ourselves, so we can see here it's finished. In fact, let me just show you here. If we do a hex dump, -n, let's, or -c to show the ASCII, and let's do 100 bytes of it. You can see that it is in fact a MP4 movie. So it's not a PE file, and that would explain what they're doing in the next step here, which looks like some sort of decryption. So back here, they've downloaded that porn video, that MP4, and they are now iterating through the resource. So this is the resource length, so var length, and this is a counter. Resource count. So while they iterate byte by byte through the resource, and once they reach the end, they break. For each iteration, they grab the downloaded file, the MP4 file. So we could actually name this var pornvid. So they grab the pornvid at another counter. So let's call this named var porn vid counter. Okay, so they have this porn vid counter, and they copy a byte into this temp byte here. So let's name this var temp porn byte. Then what they do is they increase the porn vid counter not by 1, but by this interesting math that they've done previously, which is the number of times the resource fits into the data that they downloaded. So it's some offset. So like, let's say if it's 10 times bigger, this value is 10. So it grabs every 10th byte from the MP4 video instead of every single byte. So it's very interesting how they've done this. What it allows them to do is it allows them to map the key that they're using for this XOR across the entire movie. Instead of just using the first, X number of bytes, they actually use the entire movie up to that limit that we saw here, this 0xa something something something, as the key. And they skip every few bytes. So like I said, for example, if it's 10 times larger, they skip every 10 bytes, or if it's 5 times larger, every 5 bytes. And then every 5th byte is a decryption XOR key for the resource. Now, that also explains why when we look at the resource, it's not completely obfuscated. Because many of these bytes are going to be null bytes. I mean, it's an MP4 video, so there's lots of null bytes in there. So for each null byte, obviously, it's an identity XOR. So it's the same, it creates the same byte. It doesn't alter the byte that it's XORed with. So because it's an MP4 video, lots of null bytes, lots of the PE file remains the same, even though it's XOR encrypted. So that's kind of cool. And if we just finish walking through the XOR here, so for each byte, at that offset interval in the porn vid, they XOR it with the resource, and then obviously copy it back into the resource. And then once they're done, they close the handle and jump back. So let's call this function name malware decrypt resource. Okay, and now they have a decrypted resource that they can write out to this temp file and then create the process for it. So why don't we see if we could reproduce this in Python? I'll grab the data file, I'll grab the resource. So let's actually copy the resource out now. I'll dump it out to a file with resource hacker, right click, save.bin, save that out, close that up. And let's pop over to our command line here and see if we can't create some magic. So let's look at our directory here. Python, our resource, And what did we call it? Read file in. The porn vid is that MP4 file. So that is right here. Read binary, read it in. Okay, so now we have to get the multiple between the two of them. So let's do hex of the length of the porn divided by the length of the resource. Okay, so 24C and let's see if the length of the porn is bigger than, let's do hex for that. So that's actually bigger than the value here. So it's actually bigger than this. So the size of the porn video is actually truncated down to that size. So let's do porn size equals this. Okay. So then let's do the hex of the porn size divided by the length of the resource, just like we had before. Okay, so that's our offset bytes. So every hex 1E bytes are the bytes that we actually select from the MP4 porn video. So let's create our little outstream here, and let's do for I in range len of the resource, and out plus equals char of, so we have to turn it into an ord. I'm using Python 2.7, Python 2.7 for life.
Get off my lawn.
XORed with an ord, and let's fill these in. So the first iterator is going to be across the resource. So we're going to do resource at I, because we XOR with every byte for the resource. And for the porn, we XOR at every byte. So IX times the offset, which is 0x1e. Okay, so now this should select every 0x1e bytes in the MP4 video, so every byte that's spaced out by that amount, and XOR with every single byte in the resource in order to produce our decrypted PE file. So let's see if we can get this out. Let's print out a few bytes here to make sure that we did it right. Let's print out 500 maybe. Hey, that looks good. So it corrected, instead of MN, it's now MZ. And it looks like that's a good header here, at least for a P file. So let's write this out and we'll take a look at it in IDA and see what we got. Out.bin, write binary, write out. Okay, and we'll take a look at this in IDA. Oh, looks like we've got a PDB path, so that looks good. Hey, looks like it's loading up, no problem. Do we have imports? Yes, we do. So we have a well-formed PE file. Excellent. Now you might be wondering, why does it look so crazy like this? Well, I think that's because it's VB6. And if we look at the imports here, yeah, it's definitely VB6. So this is a VB6 file that is the output from that very interesting loader. And what we can do is see if this is packed. I'll just upload it to UnPackMe.
UnPackMe.
And see. And let's see here. Out. Turn it up. Hey, look at that. It unpacked, no problem. And it's Emotet. So the reason why I want to talk about the sample is that I think it's really interesting. I think it's one of the first times I've seen that type of external key data being used to decrypt a payload. So even if you have the sample and you're analyzing it statically, you're not going to be able to decrypt it unless you go and make that call out to the porn site and download the MP4. I also think it's very interesting because the MP4 file is benign. I mean, there's nothing wrong with it besides it being a terrible porn. Nothing wrong with porn, just that particular porn is pretty bizarre. So without that porn video, you can't decrypt the sample. And so basically on its own, that MP4 is perfectly fine, it's valid. But it also is the key for this packed and encrypted PE file, which happens to be Emotet. Now, I think this is very interesting. I think there could be more of this sort of stuff in the future. It is a pretty decent way to beat static analysis, as you can tell here. It works really well. And the only way to really circumvent this is to have this run in a sandbox which has full internet access. And of course, if that movie was ever taken down, you wouldn't be able to decrypt the payload at all. So it's very interesting. I think it's clever on the part of the malware developers. It's a clever strategy. And I'm going to be looking for more of this kind of stuff. I think it's very interesting. I also, one note about this that is probably something that's going through people's minds. This is a simple XOR, and a lot of the PE file was in plain text because the XOR key had a lot of null bytes in it. Now, that might lead you to think that you could brute force the key. It's not true. The way that they set this up is incredibly clever. Because they've used the entire MP4 file and they've spread the key across the whole thing, there's no repeating key material. It's not like they have a set cipher stream that's reused across the entire PE file where you could use some sort of crib to guess what that cipher stream is and then reuse it to decrypt the rest of the PE file. It wouldn't work. What they've effectively created is a key that is the length of the data, random key. So trying to brute force that it doesn't seem possible, to be honest. So this is actually, even though it looks janky and it looks, easily breakable, it's actually very clever and well designed. I just want to note that just because obviously if you see like single byte XOR, you think, this is garbage. I don't even care about the MP4 file. And in this case, actually, you would need it to recover the full PE file. Okay, so with that, we'll wrap up. As always, I'll put all the links to the samples, scripts, everything in the video description below. Like and subscribe. Let us know what you want to see next, and I will try and get a few more of these videos out to you guys on a little bit more regular basis. Again, still lots of renovations, little puppy in the house, and obviously, busy with work and unpacking and everything else, but I'll be trying. So until next time, keep exposing the mechanics behind the malware. Stay curious. Bye.
Yeah, you know you fucking feel me. Yeah, you know you fucking feel me. Yeah, you know you fucking feel me, right?